So welcome to the lecture. We will continue from the previous lecture. Before proceeding, let us point out this useful reference. You can consult this book by Ohani and Ruffini for additional details regarding what we have discussed in the previous lecture, as well as what we are going to discuss in this lecture and in several subsequent lectures in this module. So let's start with a brief recap. So what we have done in the previous lecture, we started from electrostatic, and then we arrive at the Maxwell's equation by imposing certain physical conditions. That is Lorentz covariance, restriction on the number of derivatives in the equation of motion. Equation of motion has to be only second order in derivative, both in space and time, and there are no exponentially growing or damped solution, as well as there are no oscillatory solution for a static charge distribution. We only have 1 over r kind of potential for them, and the conservation of charge, that is del mu j mu equal to 0. We have to impose this continuity equation, and given this set of condition, we get our familiar Maxwell's equation purely from the equation of electrostatics. And we have also seen that this Maxwell's equation enjoys a gauge symmetry. That is, if you transform your gauge field to some a prime mu from a mu nu, and the new gauge field a prime is related with the old one this way, where chi is an arbitrary function of space-time coordinate, and this chi is generating the gauge transformation, the Maxwell's equation remains intact. And we demand that this is a fundamental symmetry of this theory, and all the interaction between electromagnetic field and that of any other matter should respect this gauge symmetry, and we will see the consequence of it in this lecture. So what we are going to do now, again, we will start from electrostatic and try to figure out the equation of motion of a point charge coupled to a background electromagnetic field, which should be consistent with the Lorentz covariance, as well as should be invariant under this gauge transformation. Let's try to do that exercise. So we'll start from a static point charge. In the non-relativistic limit, the Newton's second law for this point charge will be rate of change of 3 momentum dp dt is equal to minus q. Q is the charge of this point particle, gradient of the scalar potential, right? Also note that the direction of p is governed by this gradient rate. It will be useful to come up with the correct indices when we are going to write down the Lorentz covariance version of the equation. So now we wanted to make this Lorentz covariance first. So remember, this side is the derivative of the scalar potential, but we know from our previous discussion that scalar potential together with the free vector potential from the 4 vector, which we call the Maxwell gauge mu, right? So this side must be replaced by derivative of this delta mu, derivative of this mu, sorry. Right. So we'll have something like this if you want to make a Lorentz covariant version of this equation. On the other hand, the left hand side is easy to guess. We will have just the dp mu d tau. Tau is the proper time which is invariant. So this is the natural generalization. But remember that here the free index on P should come off the free index from this del. So this index on nu, on the gauge field should be contracted, because we should have the same free index in both sides of the E. Otherwise, they will not transform in the same way. So we demand that if you contract it with the for velocity mu, put Q by C front. This is the correct Lorentz covariance generalization of this equation. Remember, U mu for relativistic for velocity, the zeroth component gamma times C, and the C component gamma times C. V is the three velocity with which this point charge is moving in the left. So in the non-relativistic limit, if you take a look at the spatial component of the equation, that is mu equal to I component, and in that limit where all these v's are very, very smaller than C, gamma is equal to 1. So remember, gamma is 1 minus v square by c square raised to the power minus half. V by c is very, very small, so gamma tends to in that non-relativistic limit. Tau with t. So if you look at this, then you can easily see that this equation b does d tau, and from this side we have q by c, and if you expand this sum over nu, we will get u0 del I a0 plus ui del I ai. But now ui is basically v of I, and u0 is basically c in the non-relativistic limit. So u0, this term is the dominant term. This term we can neglect in the non-relativistic limit. So we have q by c, and u0 is basically c. From here you can see, and c then u I, and a0 is basically capital phi. So you have q, sorry, a0, but remember a0 is the down index. So when you raise and lower the zeroth index, there will be a sign. A0 is actually minus of capital phi. Will be c times capital phi delta I of, which we are just going to write it this way. And you can see that we get back our equation from electrostatics. Okay. But notice that although this is the correct Lorentz covariance generalization of this equation, we have to make sure that this equation should remain invariant under the gauge transform. Now remember that gauge transformation is given by this. So you can easily see that if you change this mu accordingly, this equation does not remain invariant under gauge transform. So although this is a Lorentz covariant, but it is not invariant under gauge transform. So we have to rectify that. Okay. But not invariant under gauge transformation. So we have to rectify. Let's do that. So now you can see that we have to just replace this combination by suitable combination, which will remain gauge invariant. And we can easily guess what can that be. that is nothing but the Maxwell field strength, F mu. Instead of just del mu mu, we should have used F mu. That will do the job. Let's do that. So we have dt mu d tau q by c u nu f mu, and f mu, remember, is defined as del mu nu minus del nu nu. Basically, we have added this additional term, right? Remember that again, this equation will reduce in the non-relativistic limit to this equation. We have already shown that this equation correctly reduces to this equation, and you can easily see that even if we add this del nu a mu term with the indices contracted with nu, etc., again will reduce to this equation. The reason is very simple. If you look at mu equal to I index, so if this mu of f mu nu will be I, because f mu nu is antisymmetric, so nu can only be 0. Right? If nu is again I, then it will automatically 0 because of this anti. And you will again get effectively, when you look at mu equal to I index, you will effectively get u nu contracted with del mu nu, and then it will reduce it to the corresponding Newton's second law in the for this charge point charge in the non-relativistic. Also, this equation is the correct equation in the sense that this remains invariant under Gauss transform, because if mu nu remains invariant under Gauss. But let's rewrite this equation a bit to get little bit more insight. Remember, ideally, this equation is the rate of change of this momentum is sourced by the derivative of the field. If only one term involving derivative of it, right? Let's try to see that whether we can make this equation similar to that form. So rate of change of something is equal to derivative of just a mu. Right now we have two terms actually. Let's try to manipulate. So let's rewrite explicitly the two terms. One is mu del mu a nu minus u by c mu del mu a nu. But now what is this? Remember, mu is basically the tangent vector to the wall line of the point particle, which is nothing but dx mu d tau. This wall line is now parameterized by the proper time tau, and this is nothing but d tau del mu, and what is this effectively? Now, if you use the chain rule, then we'll be able to write it as u by c. This combination acting on a mu nu will be just dA mu d-tau. Okay. Now you can see we can take this term to the other side and combine with mu. So if you do that, you have d-tau dd tau of p mu nu plus q by c. A mu nu is equal to q by c mu nu del mu mu. Now, if you look at this equation, this is of the similar form what we have written here. So this side is basically what you have expected, some Q by C factor, then there is a derivative of gauge field and the free index will be contracted with ME. This is what you have guessed while trying to Lorentz covariantize this electrostatic equation. This is what you would have expected. But now the fact that this equation has to respect the gauge symmetry, this side is not just the rate of change of kinematical momentum p mu nu of the point particle. Rather, this side is rate of change of this entire thing. Our contribution is coming from the gauge field itself. And this thing p mu nu plus q by c mu nu, we write it as pi mu nu and this pi mu nu we call it the canonical momentum. So remember, for point particle p mu nu, the kinematical momentum is just m times mu, but canonical momentum is this kinematical momentum plus a contribution coming from the field itself. This is canonical moment. And this is a very important lesson that we learned. So the for the case where the potential, for example, for this case, it's a potential of a point particle interacting with the electromagnetic field is velocity dependent, then the equation should not just be the rate of change of the kinematical momentum, it should be rate of change of the canonical moment, which is kinematical momentum plus a contribution of the field. And this is true not just for electromagnetic field, as long as you will have a velocity dependent potential, that is the coupling with the field or the point particle involves the velocity of the point particle, and that equation is consistent with the underlying gauge symmetry. You will always have the rate of change of the total or the canonical moment. We will see that this will be the case for the gravity also in the subsequent lecture. So now what we will going to do based on these lessons that we learned from this warm-up exercises in this lecture and the previous lecture, we are going to use them to get a Lorentz covariant generalization of Newton's theory of gravity, and that we will start doing from the next lecture. We will end here and thank you for listening.